force on a moving charge. In a magnetic field. In the first two lessons, we discussed about charges, electric charges
Yes.
in electrostatics,
Force.
where we only discussed about the static charges,
Yes.
the charges at rest. Those charges, they only produce electric field. The charges at rest, they only produce electric field, whereas the moving charges, they produce a magnetic field around them. Magnetic field. For example, suppose an electron, if the electron is moving in, okay, whether it is moving in magnetic, external magnetic field or not, whatever it may be, whenever an electron is moving, it produces a magnetic field around it. Okay, there is a magnetic field enclosed by the charge, moving charge. Okay, similarly, any charged particle, they produce a magnetic field around it. They produce a magnetic field whenever they move with the velocity. Okay, whenever they are in motion, or whether they are in accelerated motion or with a uniform motion, no problem at all. They produce magnetic field. Okay, these magnetic fields will be tested by another external magnetic field. Okay, this magnetic field produced by the particular charge. Okay, they act as a magnetic dipole. Okay, otherwise they act as a tiny magnet. Tiny magnet. Okay, the charged particles, they become a tiny magnet. When these tiny magnets, they move in another magnetic field, they experience a magnetic force. So that is what we are going to discuss. Force on magnetic field force on a moving charge in a magnetic field. So this force is only experienced by the charged particles. Okay, the neutral particles, they don't experience magnetic force. Only charged particles experience magnetic force. Okay, neutral atom, neutral molecule, chargeless particles like neutron, photon and all, they don't experience this force. Only charged particle. Okay.
Yes.
Okay, now we are going to discuss about the mathematics behind this concept. So consider this as y-axis and this as x-axis. See, we have a plane. Okay, this plane consider this as x-axis and this is y-axis. Okay, this is y-axis and we have a magnetic field in the x direction. Okay, now our magnetic field is pointing in the x direction. Okay, the charged particle now moving with a velocity in xy plane. Okay, it is moving in xy plane. With the velocity and making an angle theta with the x-axis. Otherwise, making an angle theta with the magnetic field. Okay,
Yes.
the charged particle moving in xy plane, and we have z-axis in the perpendicular direction. Okay, it is perpendicular to the xy plane. We have an z-axis. Z-axis. Okay, bye. So this is z-axis. So magnetic field in the x direction, and y direction we just leave it. Okay, now what happens now? The magnetic force experienced by the charged particle. Charged particle, it experiences a force. Actually, this force is proportional to magnetic field. Okay, the magnitude of the magnetic field, and it is proportional to the speed of the particle. Okay, and then it is proportional to the charge of the particle, and also directly proportional to the sine of the angle between V and B. Okay, the magnetic force experienced by the charged particle when it is moving in the external magnetic field there, it is depending on all the four quantities. Okay, dQv and sin theta. Therefore, F equals to dQv sin theta. Okay, there is no proof for this particular equation. We only have equation. That's right. There is no derivation for this. Okay, just memorize the equation dQv sin theta. Okay, we know force is a vector quantity. Okay, so we are going to write this equation in vector form. Okay, here Q is scalar, B and V are vectors. Okay, you just write this equation like such that Q V cross B as a vector cross product. B cross B. Do you understand?
Yes, sir.
See, in this case, we are going to find the direction of magnetic field. So the direction of magnetic field is found using right hand curl rule. Okay, right hand
Cool.
curl rule or Fleming's left hand rule or right hand palm rule. Okay, you can go for any one method. Okay, right hand curl rule, Fleming's right hand palm rule or right hand, Fleming's left hand rule. Okay, now go for Fleming's left hand rule. Okay, Fleming's left hand rule, what does it represent? Actually, in this case, if you go for Fleming's left hand rule and right hand palm rule, no, the angle between V and B must be 90 degree. Theta must be 90 degree. Okay, in this case, if you want to use these two rules, the theta must be 90 degree. Therefore, we go for right hand curl rule. So, right hand curl rule, what does it represent? When you curve your four fingers, okay, right, four fingers of your right hand, the thumb represents the direction of force. Okay, the curled finger represents B cross B. Okay, the curled finger will represent B cross B. Okay, such that you have to curl your finger. Okay, in this case, we have to curl our finger in the downward direction, not in the upward direction, in the downward direction. Therefore, in this case, the force it is in the negative z axis. Force in negative z axis for this particular diagram. Direction of force. Suppose if I take B in the y axis for this particular case, no, the force will be in the positive z axis. Okay, I'll redraw the diagram. Suppose if I draw velocity in this plane, velocity and magnetic field in this plane, the force will be in the upward direction. Okay, this is velocity and this one is magnetic field and making an angle theta. This one represents V cross B. Q into V cross B. So this is a rule. So the same rule you might have studied in your mathematics class. Okay. You remember the vector cross product rule. Suppose if you take A cross B, so A cross B in a plane. So suppose this is a plane containing the two vectors. The C vector A cross B is in the same direction. So this one A and B, and this one is A cross B. The angle is from A to B, theta. Okay, if you just apply right hand curl rule. Okay, from A to B, if you apply the curling your finger, the four fingers, the thumb represents theta speed.
Yes.
Okay, and the previous diagram, what happened now? I have taken B in this direction. Okay, B in this direction and B in the opposite direction. Therefore, the force it is in the downward direction. That is the difference. That's all. Because we know A cross B is equal to minus B cross C. Anti-commutative.
Yes, sir.
Anti-commutative property. Okay, and you can apply Fleming's left-hand rule and the right-hand palm rule whenever they make angle 90 degree with each other. So exactly velocity and magnetic field. Now we redraw this diagram again. Okay, redraw the diagram again. Now I make the diagram little bit different. Okay, now now I go for X, Y, magnetic field in the Y direction. Okay, magnetic field in Y direction and velocity vector in the XY plane. Okay, velocity vector in the XY plane. Now we will get the answer exactly. Now the answer is the force will be in upward direction. Okay, force will be in the upward direction. That's all. So this represents the force vector and this one is B vector and the angle between B and B. Okay, no?
Yes.
Okay, now what we are going to do now? We are going to resolve the velocity vector. Okay, resolve the velocity vector into the components. Okay, when you resolve this velocity vector now, you will get horizontal and vertical components. Okay, horizontal component in the x-axis. Horizontal component in the x-axis and vertical component in the y-axis. You understand?
Yes.
So this one is V perpendicular and this one is V parallel. Okay, V parallel. In this situation, V parallel, okay, V parallel making an angle theta 0 degree with B. Correct?
Yes,
V
sir.
perpendicular makes an angle 90 degree with B. Okay, only this component is working with the magnetic field, not this one. Okay, the component parallel to the magnetic field, it is unused. Only the component perpendicular to the magnetic field will be used. Okay, ma?
Yes, sir.
So this component, perpendicular component is V sin theta. Parallel component is V cos theta. Okay, don't worry about the parallel component because parallel component, there is no force. Okay, because of this parallel component, there is no force in the force due to the parallel component. Okay, the force due to the parallel component is 0. Okay, only we will get the force because of the perpendicular. So that is why the force is equal to BQV sin theta, not simply BQV.
Okay.
Therefore, the force is maximum. F is maximum when theta equals to 90 degree. Okay, now you can redraw the diagram. Okay, now you just redraw the diagram. So in the x-axis draw velocity vector, and in the y-axis draw magnetic field vector, and in the exactly z-axis we will get force. There is no difference in this case. Here it is magnetic field vector, and here it is velocity vector. Here angle theta equal to 90 degree. 90 degree, and we are getting force. Okay, ma?
Yes, sir.
So suppose if the particle, if the charged particle moves perpendicular to the magnetic field. Okay, if the charged particle moves perpendicular to the magnetic field, it experiences the maximum force.
Yes.
Okay, suppose if the charged particle moves parallel to the field, if B is parallel to B, theta equal to 0 degree, therefore force equal to 0. It will not experience any force.
Okay.
Okay. And one more thing. The third thing is when theta is not equal to 0 or 90 degree. Okay, if theta is greater than 0 and less than 90 degree. So arbitrary. So it's any angle. Okay, in this particular case, the particle will have both the components. Okay, both the components. V parallel, it will not experience any magnetic force, but it produces linear motion. You understand?
Yes, sir.
And V perpendicular. Perpendicular deflects the charged particle. Charged particle in V. So that we will discuss one by one. Okay. In case of the angle theta, which is not 90 degree, which is less than 90 degree, our charged particle will experience the combined effect. It will experience a combined effect. Therefore, it will move in a spiral path. Sorry, not spiral path, helical path. Moves in helical path. That we will discuss one by one. In this case, 90 degree, no, here the object will move in circular path. Circular path. Okay. We'll see the topics one by one. So when theta 90 degree, you can go for Fleming left hand rule or right hand palm rule. Do you remember the two rules? Left hand rule and right hand palm rule? No doubts, no?
Yes. Yes.
Okay. And based on this concept, you can define the SI unit of magnetic field. Okay, we know F is equal to BQV sin theta. Okay, the magnetic field SI unit is Tesla. Okay, we are going to define 1 Tesla. Defining SI unit of magnetic field. That is 1 Tesla. How shall we explain? F is equal to BQV sin theta. See, in this case, the charged particle of 1 coulomb, it means unit charge. Unit charge moving with the unit velocity, 1 meter per second. Unit velocity. Perpendicular to the magnetic field. Okay. The charged particle is moving with a velocity of 1 meter per second. The magnitude of the charge is 1 coulomb. It experiences a force. Okay, it experiences a force that is produced by 1 Tesla. Okay, we will see one by one. So suppose if I insert all the values, okay, F is equal to B into 1 into 1 into 1. Okay, everything becomes B. So therefore, F becomes B. Therefore, we can define the force acting. The force acting on a charge, on a unit charge, on a unit charge moving with a unit velocity right angles to the direction of. 1 minute. Hello.
Yes, sir.
Okay, we continue. Okay, so 1 Tesla, it is the magnetic field. Okay, that can be that is used to produce a force on a unit charge moving with a unit velocity. It is right angle to the direction of field. Okay, that is what 1 Tesla. Okay, and we have one more unit called Gauss. Gauss for magnetic field, which is having some conversion. 1 Gauss is equal to 10 power minus 4 Tesla. Okay, 1 Gauss is equal to 10 power minus 4 Tesla. Sometimes they ask in problems. Okay, 1 Gauss is equal to 10 power minus 4 Tesla. Okay, next we'll go for Lorentz force. Lorentz force. So this one is combined effect. Okay, whenever a charged particle moving in both electric and magnetic field. Okay, electric and magnetic field. Okay, it experiences a combined effect. Okay, net force will be acting on the charged particle. So the net force F equals to QE vector plus QB cross B vector. So this net force will be acting on the charged particle, which is called as Lorentz force. Okay, so it is combined effect, electric force and magnetic force. Together it is called as charged Lorentz force, but we have only this particular topic only. So no more further explanations in this particular topic. So Lorentz force is nothing but, I think sometimes they simply call magnetic forces Lorentz force also. Simply BQV. BQV is also Lorentz force.
Oh,
So somewhere after sometimes we will see simply Lorentz force is BQV. And this one will also be called as Lorentz force, the combined effect. Okay, next we'll come to the next part. The work done by magnetic force. Work done by magnetic force. we know in normal mechanics, okay, in mechanics, whenever an object is acted by a force, it will make some displacement. Okay. So when you multiply the displacement with the force, you will come to the work done. Okay, do you remember?
Yes, sir.
So that an object of mass m, whenever it is acted by a force, it produces some displacement in both some extent s. So work done is equal to F into S. We
Yes.
know. But here in this case, no, a charged particle, okay, it is moving in a magnetic field. Okay, magnetic field, it experiences a force in one particular direction. Whether
Yes.
this force, okay, this force will make any work done on the system, that we are going to discuss. We know the relation between power and work done. Okay, power and work done relation. Do you remember? Our power and work done. Power is the rate of doing work. Okay, P equals to dW by dt. Do you remember?
Yes, sir.
Power is rate of doing work. So rearrange this equation. dW equals to P into dt. Okay. And we know in mechanics the power is expressed as force and V, F dot V, the
Hmm.
dot product of force multiplied by velocity. Okay, now integrate this one, both sides. W becomes integral P dt. Okay, now replace the value. W equals to integral, instead of P, F dot V dt. Okay, F dot V dt. Now go for the next page. Okay, now we know the formula for force, magnetic force. Q
E.
V cross B.
Yes.
Q V cross B. Now you just replace the work done formula. W equals to integral Q V cross B dot B dt. Now take the Q outside, okay, out of the integral, and this one is a triple product, vector triple product. Okay, did you study this concept in mathematics? Vector triple product.
Yes,
Any
sir.
idea?
Uh,
We have some identities. Okay, we have some properties in vector product, in vector triple product. Okay, we have a direct formula also. A cross B dot E equals to 0. Okay, now we will explain this concept, why it becomes 0. Uh, what is the direction of A cross B? Suppose if you take A vector
hmm.
and B vector. So just now we discussed angle theta. A vector cross B vector. The answer A cross B
So,
is perpendicular to both A as well as B. So it is perpendicular to both A and B.
yes.
Okay. Now the angle between A cross B and A, it is 90 degree.
Yes, sir.
Okay, angle theta equals to, not theta, angle between A cross B and A is 90 degree. In case of dot product, suppose if I take this as C dot A, C dot A, which is equal to CA cos theta. Okay, here you have to insert 90 degree in theta. Cos 90, which is equal to 0. Okay. Do you understand this one?
Yes. Yes.
So whenever a cross product, okay, cross product, it is again multiplied with the same value in the brackets. Okay, it results 0 only. Because V cross B is perpendicular to V cross B. So the direction of the V cross B vector is perpendicular to V. Okay, V cross B perpendicular to V vector. Therefore, the entire product is equal to 0. The W becomes 0. That's all. Okay. It means that there is no change in kinetic energy. There is no change in kinetic energy. Kinetic energy remains constant. Ke is constant. They ask the question like, in case of magnetic force acting on the system, the kinetic energy remains same, or that there is no change in kinetic energy, or the work done is equal to 0. They ask any kind of question. This is because B cross B dot B becomes 0. See, this case is applicable in case of circular motion. Okay, whenever an object in circular motion, the centripetal force is acting in this particular direction.
Yes.
Okay, and velocity vector perpendicular to centripetal force. Therefore, centripetal force will not do any work on the system. Okay, the centripetal force, it only deflects the particle. Okay, it only deflects the particle. It will not do any work on the system. So in this case also, work is equal to 0. Suppose if you see the motion of the planets around the sun will not do any work on the planets. Okay, only the gravitational force will make the circular path. They only make the circular motion. They don't do any change in kinetic energy. That's all. So this question is the work done by magnetic forces 0. Yes, 0. We know work energy theorem. Work energy theorem. Do you remember work energy theorem?
Sir,
You might have studied. Work done on the system produces change in kinetic energy. Okay, work done on the system, change in kinetic energy. W0 means change in kinetic energy is also 0. Okay, no?
sir, something K initial and K final. Sir.
Yeah, K final minus K initial equals to 0.
Yes.
Delta K equals to K final minus K initial. If this is equal to 0, K initial equal to K final.
Yes.
No change. No change in kinetic. That is why it becomes constant. Okay, no?
Yes.
Okay, so next we will go for the next topic, motion in uniform magnetic field. What exactly the track of the charged particle in the magnetic field? Motion in uniform magnetic field. Here we have three cases. Already I stated theta equal to 0 degree and 90 degree and any angle. Any angle between 0 and 90. Okay, not exactly equal. Okay, we have three angles. We will see one by one. Okay, first case is when theta equal to 0 degree. Theta equal to 0. It means V is parallel to magnetic field. V vector is parallel to magnetic field. Therefore, the force experienced by the charged particle is 0. If F is equal to, F is equal to BQV sin theta. Here sin theta is 0. So BQV 0. Therefore, the total force acting on the charged particle is 0. So it means that the charged particle will go inside the magnetic field without deflection. It will not experience any deviation. It moves in the same straight line path. When the velocity vector makes angle 90-degree with a D, magnetic field vector. So now we will see one by one. Okay, we have a region. Okay, here the magnetic field is it is passing into the plane. Okay, suppose if you look at your textbook or the notebook, no, the field is passing into the plane of paper normally. Okay, B is inside. It is passing inside the plane of paper. Suppose a charged particle is moving in the plane. Suppose if it is X and Y, XY plane, charged particle moving in the XY plane means, suppose consider a charge Q. It is moving with a velocity V in this plane. What happens now? V is perpendicular to B. It is always perpendicular. What happens now? The charged particle will experience a force. Okay, but for this case, you just apply Fleming's left-hand rule. Okay, Fleming's left-hand rule. The magnetic field is into the paper. Okay, our forefinger will represents the direction of magnetic field, and middle finger will represent the direction of velocity of the charged particle, and thumb. Okay, in this particular case, if you point your forefinger, okay, into the plane of paper, the thumb will represent the force which is acting in the upward direction.
Yes, sir.
Okay, you will experience force in the upward direction for this case. So momentarily, the charged particle will move in this direction. Okay, and then again it will experience a force. Okay, similarly, the charged particle will experience in each second. Okay, every second it will experience a force. The force will make the particle in the sideways direction. Okay, if you see the entire thing as together, no, we will see a circular motion of the charged particle inside the magnetic field. So if suppose the charged particle, when it is in this particular direction,
Yes.
the force will be towards the center of the circle. So therefore, every time the charged particle will experience a sideways force. Therefore, it makes a circular motion. It will make a circular motion inside the magnetic field. When it is perpendicular to the magnetic field, the charged particle will experience a circular motion. Circular motion. Okay.
Yes.
Now we'll come to the point. Okay. In case of circular motion, there must be the centripetal force acting on this particle. Okay, suppose the charged particle having a mass m and charge q, the charged particle will experience a centripetal force which is provided by the magnetic force. Okay, here theta is 90-degree. Therefore, the centripetal force, which is mv square by r, suppose if I take the radius as small r, Okay, m is the mass of the charged particle, v is the linear velocity, which is equal to bqv, bqv, and v square and get cancelled, or radius of the charged particle. Okay, radius made by the charged particle is equal to mv divided by dq. mv divided by dq. Okay, it means that r is proportional to v. So as you increase the velocity of the charged particle, the radius becomes higher. Okay, also it is, suppose you just rearrange this equation, v divided by b q by m. Have you ever seen this quantity q by m? R is inversely proportional to q by m. Q by m, do you remember this quantity? Charge per mass, which is equal to specific charge. Specific charge or charge to mass ratio. Charge to mass ratio. Okay, this quantity is essential in identifying the charges. Okay, whether the charge is a proton or electron, it can be identified with the help of the charge to mass ratio. Okay, sometimes we will get problems based on this particular topic. Okay, radius is depending on the charge to mass ratio, otherwise the velocity of the particle. Now I'll go for the time period of the particle. Time period. Time period, we know the formula. Suppose the charged particle, it makes one revolution. Okay, one revolution in one time period. Therefore, the distance traveled is 2 pi r. Okay, which is divided by v. Now insert the value of r in this equation. Okay, or r by v. Okay, we bring this v to the left hand side, r by v, which is equal to m by bq. Okay, we know r is equal to mv divided by bq. R by v equals to m divided by bq. Therefore, time period is equal to 2 pi m divided by b. 2 pi m divided by b. See this equation. What we shall conclude from this equation? Independent of r and v. R and v. Okay, time period is independent of the radius of the particle as well as velocity of the particle. So velocity doesn't have any relation with the time period. So time period is independent of the velocity as well as radius. It is only depending on mass, magnetic field, and the charge. Okay.
Yes, sir.
And frequency. Frequency is reciprocal. F is equal to 1 by t. That's
Right.
all. The frequency, this frequency is called the cyclotron frequency. Actually, cyclotron, they deleted the topic, cyclotron frequency. Okay, it is not in our syllabus. Cyclotron is deleted. So whenever the charged particle moves perpendicular to the magnetic field, it produces a circular motion. So circular motion. Also, one more thing we discussed as a separate topic, the work done is zero.
Yes.
Work done is zero. Okay, in this particular case, theta 90 degree exactly here. Work done is zero. So what exactly is done by the magnetic force here? It only produces change in direction. Okay, no change in velocity, only change in direction of motion. So that's all. That's all with the magnetic field. Okay, we
Okay.
can actually we studied this concept in class 11 also. Suppose whenever an object is uh, okay, when an object is given a force which is perpendicular to velocity. Okay, perpendicular to velocity, it only changes the direction. Okay, no change in velocity. Okay, ma?
Yes.
So in order to increase or decrease the velocity, the force must be parallel or anti-parallel to the object. Okay, suppose an object is moving in this particular direction, the force must be given in this manner or in this manner to increase or decrease the velocity.
Yes.
In this case, V will be variable. Okay, otherwise, if uh, object is moving in this particular direction and force is acting perpendicular to the velocity, V is constant, or speed is constant. Okay, it is not velocity, it is speed. Because this changes the direction. Okay, we know velocity means speed plus direction. Okay, if any of one quantity changes, there is a change in velocity also.
Yes.
So that we should understand. Okay, whether uh, speed is changing, there is a change in velocity, or direction is alone changing, speed kept constant, that is also velocity. So any one of this particular these two quantities changes, the velocity will change. Okay, wow.
Yes.
But whenever the speed is changed, the velocity is like a tangential. It produces tangential acceleration. Tangential acceleration. Whenever the direction is alone changed, the acceleration is in. It is like a radial acceleration. It is not tangential. Radial. It is only the most of the time circular motion. It involves this kind of concepts. Circular motion. Okay, objects moving in circular motion. Okay, velocity perpendicular to centripetal force as well as the radius 90 degrees here. Okay, here speed is constant. Speed is constant. So these are very small information required for some solving some problems. Okay.
Yes.
Okay. Now we'll go for angle which is not equal to 90. So the velocity, when velocity vector makes an arbitrary angle with magnetic field. Okay, in this case, we have to go for the three coordinate system. Here in the x-axis, we have magnetic field. Magnetic field pointing in the x-axis. And charged particle is entering into in the xy plane. So y plane, this one is z axis. Xy plane, z axis. So the charged particle makes an angle theta with the magnetic field. The velocity makes theta with the magnetic. Okay, now resolve the velocity vector into the components. Okay, because the velocity is not perpendicular to the magnetic field. Therefore, we have to resolve the velocity vector, okay, in horizontal and vertical direction. Okay, horizontal and vertical component. Therefore, V parallel equal to V cos theta. V parallel is V cos theta. V perpendicular is V sin theta. Do you know how to resolve this component? Do you remember?
I'm not sure.
Not sure. Okay, I'll explain. Okay, this one is the vector, actual vector, V vector. Okay, this one is nothing but it is your hypotenuse. That's all. Hypotenuse of the right angle triangle. Okay, this one is your adjacent side. Actually, this one is your opposite side. So that is why we call this as rectangular component. Okay, rectangular component. Okay, this one is Vx, Vx, Vy. Vx is V perpendicular. V parallel, V perpendicular. So this one is angle theta. Okay, so you just consider this right angle triangle. Right angle triangle. If you take sin theta, opposite is Vy. So Vy by V. Cos theta it is adjacent, Vx divided by V. Therefore, Vx equal to V cos theta, Vy equal to V sin theta. That's all. Okay, the parallel component cos theta, perpendicular component sin theta. So the only thing is, see, most of the time, the angle is with the horizontal. So 99% of the time in physics, okay, concepts, no, you always get the angle theta with the horizontal axis. It means that the parallel component is always cos theta. That's all. V component is V cos theta. So only very rare case they go for the angle theta with the vertical axis. So 99% it is with the horizontal axis only. Okay. So that is why the horizontal component always it has cos theta value and the vertical component has sin theta value. That's all. Okay, now come to the point. Already I told you V parallel produces linear motion. So parallel component produces linear motion because the component which is parallel to the magnetic field, it is not affected by magnetic field. Okay, V parallel is unaffected by magnetic field. Do you understand this one?
Yes, sir.
And V perpendicular produces circular motion. Okay, the combined effect will be now. Okay, therefore, this component will make the object to move in the circular motion. And actually, they don't actually exactly produce. Okay, they try to make linear motion. Also, they try to make circular motion. Okay.
Yes, sir.
So that is why we will get a combined motion. Combined motion. See, in this case, if the charged particle enters in XY plane, no, actually, it produces a circular motion in YZ plane. Okay, circular motion in YZ plane for this particular diagram. Okay, circular motion in the YZ plane. Therefore, the charged particle will have a circle in this particular direction. Okay, and what happens now as the charged particle moves in the circular motion, the parallel component it tries to make the linear motion. Therefore, the object will make a helical motion. The object will move in the helical motion. Therefore, the trajectory of the charged particle will be looking like this. Okay, the charged particle will undergo a helical motion because of the combined effect.
Yes.
The combined effect make the helical motion. The charged particle will make the circular motion in the XY plane, YZ plane. Okay, circular motion in the YZ plane and linear motion in the x-axis. Okay, linear motion in the x-axis. Okay, again we'll go for the equations. Okay, now I'll go for the equations, but in this case, we have to resolve the values. Okay, V perpendicular equal to V sin theta, V parallel equal to V cos theta. Okay, this one makes circular motion, this one makes straight line motion.
Yes.
Okay, for this particular case now, MV perpendicular square divided by R equals to BQ V perpendicular. Is it right?
Yes, sir.
Okay, now rearrange. Now rearrange the values B to V. So cancel the square. Therefore, R equals to MV perpendicular divided by BQ. V perpendicular is V sin theta. MV sin theta divided by BQ. Okay, the radius of the circular motion is MV sin theta divided by BQ. Then time period. Time period T equal to 2 pi R divided by V perpendicular. Okay, 2 pi R divided by V perpendicular. Now you just see, you bring this V perpendicular to the left hand side. Okay, M divided by BQ. M divided by BQ. Therefore, 2 pi M divided by BQ. That's all. There is no sign terms in this particular equation. Time period. Yeah, wait. 2 pi M, B, M, B. Yeah, 2 pi M divided by BQ. 2 pi M divided by BQ. No sign component in this particular topic.
Okay, sir.
Okay. Next, we have one more term. See this one. The charged particle is undergoing a helical motion. Okay, it is undergoing a helical motion. Okay, you see during one time period time. In one time period, when t is equal to one time period. Okay, which is t equal to 1 t. Okay, what happens now? This charged particle, it produces this much amount of linear motion. Okay, this much amount of linear motion in one time period. We call this line as a pitch. So pitch is the which is defined as the linear distance, which is the linear distance traveled in t time period. You understand?
Yes, sir.
Therefore, pitch is equal to v parallel into t, not v perpendicular, v parallel, because linear motion is contributed by the parallel component.
Yes, sir.
Therefore, v is v cos theta. We know time period formula 2 pi m divided by bq. Okay, therefore 2 pi m v cos theta divided by b, h. So this much amount of information we should write. So whenever the charged particle moves in a magnetic field making an angle theta with it, it is the component, velocity components must be dealt. Okay, the parallel component try to produce linear motion. The perpendicular component try to produce the circular motion. Therefore, the combined effect will come. The combined effect produces helical motion. Okay, and
Yes,
we are going to derive the radius of the circular path. So circular path, the radius again the same concept, mv square by r equal to bqv. But here instead of v, we have to take v perpendicular. Therefore, r is equal to mv sin theta by bq. Similarly, 2 pi r, time period is 2 pi r divided by v perpendicular. Okay, and solving the previous equation, we will get only 2 pi m divided by bq, no sine or cosine term in this case. And we'll go for the pitch. The pitch is due to the parallel component, not due to the perpendicular, only due to the parallel component.